The time of projecting point clouds to camera images is over. Let me show you what replaces it. Hi, I'm Jeremy Cohen, and today let's talk bird eye view and sensor fusion. Every self-driving car has cameras and LiDAR, right? But fusing them together is one of the hardest problems in perception, and most approaches get it wrong. In this video, I'm going to show you exactly why and walk you through BEV Fusion, the architecture that solves it properly and bootstraps the entire generation of end-to-end algorithms. So let's start with the problem. A camera gives you a 2D image. It's rich in color, there's good texture, semantic information. A LiDAR gives you a 3D point cloud. It's amazing geometry. There's depth, distance estimation, and if you want to combine them, you immediately hit a dimensionality mismatch. Like one is 2D, the other is 3D, and they are not in the same space. The naive solution is to project one onto the other. You can project LiDAR point clouds on the camera image, or you can try to lift camera features into 3D, even though people don't really do that. Both of these approaches lose information in a way. So if you project your LiDAR into the camera space, you lose all the geometry of the LiDAR. And if you go the other way, you lose the rich semantic density from the camera. You're always sacrificing something. Late fusion has the same problem. If you run object detection on the camera separately and then 3D object detection on the LiDAR separately, then you combine the output boxes, you're stuck doing object detection only. You cannot build a map, do segmentation, and you throw away everything that was not a bounding box. So the question is there a common space where both sensors can meet without losing what makes each of them valuable? And the answer is yes, and the space is bird eye view. So let me tell you something. Bird eye view is a top-down 2D representation of the 3D world. You can think of it as looking straight down at the scene from above. And crucially, it preserves geometry. And here's the key insight of BEV Fusion. Instead of projecting sensors into each other's space, you transform both of them into a common representation. You build a common ground. Now, I'm a big book lover, and I read a fantastic book called The Ride of a Lifetime from the CEO of Walt Disney. And there is something incredible about him. It's like Bob Iger has realized something about Disney, is that they had you from the moment you were a child to the moment you were starting to become a teenager. And then they lost you, and then they found you again when you wanted to show Disney movies to your kids. And the thing is, they had this hole where people were disappearing from their environment. And they thought, wow, what can we do to fill that hole? You could buy Marvel and Star Wars and things like that. And so they bought Marvel. And there was a problem, is that Marvel did not want to sell Marvel. Ike, the CEO of Marvel, did not want to sell. And there is something incredible, is that Bob Iger thought about it. And he said, what is important to Marvel? And to Marvel, what was important was brand protection. We don't want to damage Marvel, the ecosystem, the characters. We want to keep this perfect. And so Bob came with this entirely new argument, which was, who could protect a brand better than Disney? We are the brand protectors. We built an ecosystem of characters and we protected them. And do you see where I'm going? It's like he came up with a common ground, which was, we are both brand protectors. If anyone should buy Marvel, it's us. And I think the common ground is what makes everything work. And in sensor fusion, even more. Rather than projecting one to the other, forcing one to the other, you make both into a common ground. So let me walk you through the stage of the architecture that does that. It's called BEV Fusion. Stage number one, encoders. Each sensor has its own encoder. So the camera uses a standard image backbone, a ResNet, something similar. It takes in the raw image and output feature maps. The LiDAR has its own encoder, so it can be a PointNet style architecture or a VoxelNet or point pillars or something that processes point cloud. And so at this stage, they are both separate and each is learning its own feature from its own input modality. Stage two is the bird eye view transformation. And this is the critical step. The most technically interesting one though. For the LiDAR, it's straightforward. You have a point cloud in 3D, so you have 3D features, and you just flatten them into the z-axis. So you collapse these features into a bird eye view, okay? For the camera, it's harder. You need to predict the depth. So you're going to do something called feature lifting. It's something I teach in my bird eye view course, and it's like you have a feature map in 2D, you are going to push these features to 3D. You're going to predict a depth value for each of these features in each of the dimensions. So that gives you a 3D feature cloud from the camera. And then you use something called BEV pooling to aggregate everything into the common ground. Okay, so on LiDAR and camera, you do something different. One, you collapse, the other, you push to 3D, then you collapse, and boom. Stage 3, fusion. And this is where the magic happens. It's almost embarrassingly simple. You have everything in bird eye view space, so to fuse that, you just concatenate. Like it's torch.cat. And it's a very basic operation. And so it also means that you could add a third sensor just as easily. Like if you have a radar and you send a point cloud, you're doing the same bird eye view transform, and then you concatenate it along the same axis. Stage 4, bird eye view encoders. Now that you have a bird eye view feature map, you want to learn from it. So after concatenation, if you have small alignments, if the camera depth distribution is not perfect, or if the LiDAR calibration had some slight errors, you run the fused bird eye view features through another encoder, a convolutional network with residual blocks that learn to compensate the misalignment, produce some kind of clean representation. Stage 5, the heads. And now this is where like your bird eye view fusion basically becomes what I call a hydranet. It's like from that single unified representation, you're going to run multiple output heads in parallel. One head for the 3D objects. It's going to use center point architecture to predict the center, the size, the rotation, the velocity. Another head for the better view map segmentation. It's going to predict a map where every single pixel is going to be classified. Drivable space, pedestrian crossing, walkways, stoplight, parking areas, lane dividers. This segmentation output is essentially a local map of the scene. So you could do somehow HD map building in bird eye view thanks to bird eye view fusion. Okay. And on top of that, from there, you can directly compute a driving path if you want. If you want to build end-to-end learning, from there you add a planning head. Okay, one real-world example that shows why this matters is Aurora. So the autonomous trucking company, they use exactly the same principle. They have all these sensors at the top, and you have HD map, radar, LiDAR, camera, etc. And they're going to put everything into an Euclidean view. It's the bird eye view. And it transforms all the sensors into a shared top-down space before then doing the fusion. So their sensor fusion network looks extraordinarily complex, but in reality, it's a one common ground every single time they move to bird eye view. So why does bird eye view fusion matter? And why should you care as an engineer? There's 3 reasons for that. First, it's lossless in a way that you do not lose data. You preserve the geometry from the LiDAR, you preserve the semantics from the camera. Nothing gets thrown away during the transformation. Second, it generalizes. You can add a new sensor type. The architecture absorbs it. You can have 6 cameras if you want, right? You don't have to have 1 camera. You can have a more realistic setup. Everything becomes about the fusion. And third, it enables multitask learning from a single network. So then you can build object, depth, segmentation, planning, etc., etc. One network, multiple heads, forward pass. If you understand bird eye view fusion, you understand the core principle behind how every major AV company does perception today. They all moved from a very classical approach where they were projecting points to the camera or where they were fusing bounding boxes. They are all of those who are moving to end-to-end learning. They are moving to things like BEV Fusion. They're fusing 6 cameras together. They're fusing it with the LiDARs. This is the heart of what I call AV 2.0, end-to-end learning. And when you think of it, everything you see with the end-to-end hysteria right now is due to bird eye view. I cover it as one of the 3 pillars of my AV 2.0. And if you'd like to full experience, I highly recommend you download it. Inside, you're going to get the entire set of 3 pillars of AV 2.0, all detailed, plain, to get you understanding AV 2.0. It's free, accessible via the link in the description. And by the way, while I'm here, I should probably be making more videos in the future. So make sure to subscribe to this channel if you don't want to miss the next one.